Hello and welcome. So today is the third day of this week. So we have been looking at the properties of laser light and their origin as well as their applications. So in the last class we looked into a couple of properties. One was the intensity, and we said that the intensity is probably the most important property of laser that has been utilized by commercial establishment industry. So today we will take it from there, and we will look at another one, and so properties of laser light and their applications. So the first thing that we will consider today is the coherence. So this is the property which differentiate a laser light from a conventional light source. In conventional light sources, what are the main source of photons? It is basically spontaneous emission in most of the cases. So the spontaneous emission by their own nature, they are not related by any phase relationship. So first place, they are scattered in various direction, and they have different phases and all. So in laser light, we have all the photons having same phase. So they are related by phase. Now if I take a device which is laser, and then we allow the light to come out and propagate. We say that okay, when it generates, it is coherent at the beginning. Okay. Now we have looked at one property, that is directionality and beam width, right. So there we said that okay, they are more or less parallel, and after certain distance they become broader, the beam width become larger. That is because of a property called divergence. So the beam does not remain collimated beyond a certain distance. That distance may be really long, and that distance can be short also. Here also, in case of this property coherence, do we have this coherence intact at infinite distance or not? So is there something like coherence time, that is, if I start here at time t equals to 0, then if I look at the beam, the same beam at some t equals to t prime, then will there still be coherence intact or not? So is there a coherence time? And related to that, I can also ask, is there a coherence length? So we will see what are these two. So what is coherence length and what is coherent time? So coherence time, this is given by this term Tc, okay, and is okay. So, where this delta nu is my emission line width. Okay. So, from upper layer to the ground level or the lower level when the transition takes place due to stimulated emission, that emission frequency will be associated with a line width. Okay. So, the spectra of that emission will be associated with a width which is known as line width. So, this is the expression for coherence time. So, when I write this expression, that means that I am telling that okay, it will not be infinitely coherent. After certain time period which is Tc, it will lose the coherence nature, okay, and the photons will not be any longer correlated in terms of phase. So, if there is a coherence time, then definitely there will be a coherence length, because up to Tc, if the beam is coherent, then the length or distance covered by photons in that period of time Tc, it will have its coherent property intact. So, therefore, that particular length scale Lc is known as coherent length, and we can very easily figure that out. This is multiplied by the speed of light. Okay. So, to be proper, if we consider the medium, then I can write C prime instead of C, where C prime equals to C by n. We have seen this earlier. So, what does that mean? That this is the length scale such that any distance shorter than this Lc, we will have the photons correlated in terms of their phases. Okay. So, these are the two terms that we will need to know. So, that is why I am mentioning them. Now, these property coherence, what are the applications of that property? So, this is one property which finds tremendous application in fundamental science. So, fundamental research, people use this coherent beams for several reasons, but when it comes to actual commercial applications, the applicability of these property is quite low. Okay, let us be honest about that. But there are still few places where the phase information is vital. Therefore, this property coherence is also of importance in those applications where, so we have heard about okay. So, now okay. So, we have heard about holography, right. So, most of us have come across this term many times, and also we have seen holographic images. Okay. So, in this particular case, when the holographic images are formed, it not only depends on the intensity of light. So, there are information stored in the holographic images. It is like a kind of a 3D image formation, right. So, there it contains the information regarding the intensity, but also contains the information about the phase, which is not there for conventional photography, the photography that we do, okay, even using our cell phone camera. So, there we do not require any phase information. In case of holography, we need this phase information. So, in this particular case we have the application of the coherent nature of laser light. Okay. So, now if I want to give you certain numbers, like how long this LC can be. This can be fairly long, like if I take a gas laser, this LC value can very easily be 100 meter. So, this is quite a big thing, you know, getting a coherent source is a big thing at the beginning, and then you can maintain the phase relationship between among the photons for a length scale as large as 100 meter. Okay. So, particularly for like gas lasers, you can get this length scale. Okay. So, this is just for your information, okay, and to get an idea about this scale, and knowing this one you can easily find out what is the length scale time scale over which the coherence sustain. Okay. So, now let us look at another property, that is monochromaticity. So, from the name itself you can understand what is monochromaticity. We have also said this one earlier, but let me just reiterate it once more. So, mono means single, chrome means color. So, the property of having a single color, that is a single frequency, is known as monochromaticity. Okay. So, at the beginning of this course we have said that laser has a property that it can be monochromatic. Okay. So, most of the lasers are monochromatic in nature. So, what does that mean? That you have while the intensity goes in this direction and frequency or the wavelength goes in the along the x axis, and then this is the corresponding frequency of the laser. Okay. And this is almost like a line. So, this property is probably most important in chemistry and physics. Okay. Particularly in chemistry it is very important. Now, I drew this spectra as like a line. Okay. Now, do we really have a line? No, we do not have. Just few minutes back we have mentioned something like line width. So, this one, though it seems like this width is like nearly 0, but actually there is a finite line width. Okay. So, if I actually look at this one, so it will look like and so you can see around this nu 0 you have a positive line width. All right. So, this line width can be fairly narrow, that we can say this is monochromatic. Okay. Nevertheless, it is not a single line, but there is a width. Now, if you ask what is the reason behind having a width, then I will very briefly tell you that there are several factors which causes this line to spread. There are things like homogeneous line width and heterogeneous line width. So, those reasons which which affects all the atoms or molecules in the laser active medium here in this context in a same or identical way, that will lead to a line broadening which is known as homogeneous line broadening. And the other causes which affect different atoms or different molecules in a different fashion, that will lead to heterogeneous line broadening. Okay. So, what are the different reasons that you can have? You can have line broadening due to pressure inhomogeneity. You can have due to the velocities of molecules in a system. So, there are other mechanisms also. The most important cause behind a line broadening which is inevitable, that means you cannot get rid of it at any cost, is what is called natural line width, or the broadening is called lifetime line broadening. So, from the name you can understand that this is related to the lifetime of energy state. So, for example, if you are dealing with an emission spectrum, so the molecule jumps from the upper state to the lower state to release photon, and you can get the corresponding spectrum. And if it is involved between these two states, I expect the spectra to be this, but it is not. Now, why? Because this state has a definite lifetime. Okay. And if you have heard about Heisenberg uncertainty principle, then you can understand that this will incorporate uncertainty in measuring the frequency, because frequency and time, they are related by uncertainty principle. Okay. So, if we cannot measure the frequency exactly, that means there is an uncertainty. And how this uncertainty is reflected in the spectrum? Uncertainty is reflected in this way, by having a width of the spectrum. So, this lifetime of a state is its intrinsic property, right, under a given condition. So, this I cannot get rid of. Therefore, the line broadening due to lifetime of a state is very, very natural to any system, and this corresponding line width is known as natural line width. You can possibly get rid of all the other sources of line broadening, but you cannot get rid of natural line width. So, the bottom line of the story is that no matter what, I will definitely have a line width for my emission spectrum, and thereby does not matter how narrow that be, there is a positive delta nu always present. Now, why I have been reiterating on this one? We have looked into the longitudinal modes, right. So, when we consider the cavity, we have seen that there are definite different frequency modes that can be supported by this cavity formed by the mirrors, are those which form standing waves. Okay. And we have also seen that there is a condition, that is this. So, for different value of m, we get different modes. So, we get first, second, third, fourth, mth, qth, different modes, and the corresponding frequency also we can calculate, right. So, this is for a particular mode. Okay. So, if I keep the same, it will be MC, all right, and I can also specify this one as lambda m and nu m. Now, I can find out say one particular mode corresponding to one particular wavelength, and then say I find mth mode, then I can have m plus 1 mode, and so on. All right. Now, I have a definite nu 0 or definite lambda 0, and then I have a definite delta nu, right. So, it is possible, depending on the delta nu value or delta lambda, okay, I can express that in either way, I can have many such modes, all right. So, my picture will look like this if I use a different color. So, these are different modes. Which modes? These are longitudinal modes. So, this one, all these are different modes. Each mode is associated with a particular color, particular wavelength or particular frequency. So, say over on this envelope, if there are 1, 2, 3, 4, 5, 6 modes that can be accommodated, then there are 6 distinct frequencies or distinct wavelengths are possible, okay. And we cannot separate them just like that. We have to do something in order to select one of them. How it is done? That is done by, so if I want to select say this particular mode, okay, I can do that by using something called ethelon. Okay. To select a particular mode, that is particular wavelength or frequency. So, this is done within the laser itself. Okay. So, we will not go into the detail of the mechanism of ethelon, but what I can tell you very simply, okay, is this particular optics ethelon, it works pretty similar to a cavity itself, okay, and cavity they support particular modes. So, thereby if this cavity is inserted into the laser cavity in a proper way, then it will select only one mode, say if it does so, and then that particular mode is being oscillating inside the cavity and getting amplified. So, I get a particular mode. Okay. So, we can choose the ethelon in such a way that I can get the particular wavelength that I want. All right. So, I can see that I can ultimately get a light output which is having very narrow line width. You can easily see that these modes are associated with the line width which are really narrow. Okay. So, we can call that as monochromatic. Okay. They are fairly monochromatic. Now, so I told you that there are several different modes, and we need to have an idea that how much is the distance in terms of frequency or wavelength between these modes. So, let us take some numbers and try to estimate that. Okay. So, so if I take a cavity length L 100 centimeter and the wavelength output of the laser or that one particular mode as 500 nanometer, which is in centimeter unit. I have this value. Okay. So, now if this is my output, then can I find out which mode it is? Okay. So, what is the value of m that we used earlier, right? So, if I have to find m, then what is the value? It is, because m lambda equals to 2L that we have seen just few minutes back. So, here 2 into 100 centimeter, and here you have the ratio becomes just a number, and if I directly give you the values, so the particular mode is this mode. Okay. So, you have so many modes before that and many modes after this. So, right now what will be the corresponding frequency? So, that we have seen earlier, that is mc by 2L. We have all the values with us, and if we put that, you can calculate. I am giving you the final result as this. So, my mth mode has the number this 4 × 10⁶. Now, if I want to find what is the wavelength or frequency of the m plus 1 mode, that is, I am looking for a mode which is all right. So, what is the wavelength or frequency, that I need to know. Okay. So, if I have to do that, so I am writing as m plus 1 instead of writing that big number. So, what I have? We have again 2L, correct, by the number of that particular mode. So, in our case this is m plus 1, and what is this m plus 1? M plus 1 is this number, correct. So, again 2 into 100, and then you get 4 this one, and if I do this division, what do I get? I get in terms of nanometer. Okay. So, you can verify this one by yourself. So, now you see the mth mode has a wavelength of 500 nanometer, and the m plus 1 has wavelength 499.999. So they are very, very closely spaced, right. So in this way you can estimate any mode, right, and also you can figure it out by yourself, or you can estimate what will be the distance between two modes. So the distance between two modes in frequency, so this is the frequency, right. So if I take nu m and nu m plus 1, we can easily figure out that delta nu. So from here we can figure out delta nu equals to c by 2l. So this is the gap between two successive modes or adjacent modes, okay, and I am talking about frequency gap. All right. So you can also, if you are given the particular characteristics of the laser, you should be able to also tell what is the gap between two particular modes. And why is it that important? That I was showing this, that okay, I have a spectra and then several modes can occur here. Okay. So how many number of modes are there that we can predict? Okay. And for different laser system, you should be able to estimate these things, right, for your own understanding. So if I take a small example, if I take the case of Heine laser. So for Heine laser, bandwidth is 1.5 gigahertz. Okay. So this is the line width of this whole envelope. Okay. So this is my 1.5 gigahertz. Okay. Giga means 10 power 9. All right. So approximately this Heine has a cavity size of approximately 10 centimeter. So what is the gap between two successive modes? So if I call that as delta nu for Heine, what is the value? That is c by 2 into 10 in centimeter. So you can also find out this one as centimeter per second, and you get it in hertz unit. So what will be the value that you will find? It is, which is 1.5 gigahertz. Perfect. So essentially what does that mean? That if I have several modes are possible, right? I can keep going in both the direction. So this gap is 1.5 gigahertz, right? Now once I figured this one out, I can tell you how many will be there. So what is the bandwidth of this one? Is 1.5 gigahertz, and this gap is also 1.5 gigahertz. So if this one is the central wavelength of Heine laser, then this is essentially the bandwidth. Let me reiterate this one. So you can easily understand that per bandwidth in Heine laser, there is only one mode for this given configuration. Suppose I would have another case, L equals to 30 centimeter. Okay. So if L would be 30 centimeter, what would be the case? Here it would be divided by 3. So in case of 30 centimeter, my delta nu would be 0.5 gigahertz. So that means this distance is now 0.5 gigahertz. So for a given bandwidth of 1.5 gigahertz, I can easily figure out that there will be 3 modes, right? Because 1.5 by 0.5 gigahertz, 3 modes. So, if I want to show separately, so it's like that. So, it will contain 3 different modes. Okay. So, in this way I can easily figure out how many modes will be there and all right. And one more thing I would like to tell you before I finish today is a quantity which is known as quality factor. You will hear this particular term whenever you try to look into a particular specific laser. Okay. So, if you look at the brochure, you will see what is the quality factor of the laser. So, this quality factor is written by this symbol Q, and it is given as this value. So, narrower the beam, narrower the frequency, essentially what I mean is, then the corresponding quality factor is very high, right. Now, it is very commonly you can get a quality factor of 10 power 8. Okay. If you take those values that I said, you can get a value of 10 power 8 or even more than that. Okay. And having a high quality factor for a laser is very, very essential, particularly in certain cases like spectroscopy and precisely high resolution spectroscopy. So, this monochromatic property of laser is something which spectroscopists really love. In industrial scale, where do we use this one? To separate isotopes. Okay. So, the isotopes have very similar absorption. Now, if you have very, very narrow line with laser light, then you can specifically excite one isotope to excited state and then use another mean to separate it from there. Okay. Otherwise, it is really difficult to separate isotopes. Okay. So, particularly in the nuclear industry, this high narrow line with lasers are routinely used to do isotopes separation. So, we will stop here today, and again we will start tomorrow. Thank you very much.